Hello and welcome to lecture 11. We are discussing about the component performance. So, in last lecture we were discussing about very important component, that is what is called turbine. We have discussed about the construction details for the turbines and we have seen we are having different kind of configuration, that is what is possible for the turbine. Then we tried to explain this expansion process on TS diagram. Similar to what all components we have discussed, we tried to discuss the turbine using control volume approach, and later on we have introduced two terminologies which are defined as say isentropic efficiency and polytropic efficiency. And we were also discussing very important aspects in terms of selection of number of stages, and we realized what all are the benefits, why we are having less number of stages for the turbine, why we are having more number of stages for the compressor. Now, let us move towards the next component. So, here this is what is representing the cut section, that is what we have used for the explanation for the performance of all components. Today, we will be discussing about the next component, that is what is say nozzle. Now, when we say nozzle, the idea will come how this nozzle will be looking like. So, here if we try to look at, this is what is representing GNX engine, where we are having two nozzles. One nozzle, that is what is called core engine nozzle, and second, that is what is my fan exit nozzle, since this is what is high bypass ratio engine. When we will be discussing the configuration about the turbofan engine, that time we will be discussing these aspects in detail. But at this moment, just say for this turbofan engine, this is what is a kind of configuration. For turbojet engine, here if you look at, this is what we are defining as our say exit nozzle. Now, for fighter planes, we will be having our nozzle, that is what will be of conversion divergence right. So, here if you look at, this is my converging passage, somewhere here we can say that is what is defined as a minimum area region, it is called throat, and this passage, that is what is representing my diverging passage. And if you look at carefully, this is representing variable area nozzle. So, we will be discussing today what is the meaning of variable area nozzle and what is the use of this variable area nozzle. In the terms, this variable area nozzle, that is also having different kind of application. So, here this is what is representing the exit of say Eurojet, the nozzle of Eurojet, that is what has been used for the thrust vectoring. So, it is not that only say the elements which are present in the aircraft or control devices, they are used for your aerodynamic control of the vehicle, but these days people they are moving beyond certain limit, and now nozzle also been used as one of the control device in order to meet special requirements. So, here this is what is representing say thrust vectoring with the different kind of structure, different kind of configuration. Okay. So, let us see what we know fundamentally. If we recall, in first week we have derived our equation for say thrust generated by the engine, that is what we have defined as say m dot into V 9 minus V infinity plus A 9 P 9 minus P infinity. We have introduced the terminology called say momentum thrust, momentum drag and pressure thrust. So, here if you look at momentum thrust and pressure thrust, that is what is representing my gross thrust, and that is what is of our interest. So, let us try to look at, suppose in this formula, this is what is representing my pressure thrust. So, question may arise, what is the use of nozzle for our aero engine? Very first, it says it is used to control the exit back pressure in order to achieve correct optimum engine performance, and that is what can be achieved by say having correct area ratio. Second purpose, that is what is, if we look at, is in terms of my exit velocity. So, it says it must efficiently convert the potential energy of the exhaust gas into kinetic energy by increasing the exhaust velocity, and by that mean it is exhausting the gas to the ambient atmosphere in an efficient expansion way. Now, this device, that's what has been connected with the aircraft. So, we need to be very much focused in terms of thrust minus drag performance. At the same time, we have seen these days people, they are started exploring different uses of this nozzle. Some of them, they are say thrust vectoring as well as for thrust reversing. Okay. So, what all are the functions? If we analyze the functions, we can say very first it is to accelerate the flow to high velocity with the minimum total pressure loss. Second, that is what is to match exit and atmospheric pressure as closely as desired. It permits the afterburner operation without affecting the main engine performance, and that is what we will be looking for, say variable area kind of nozzle. It allow for the cooling of the valves if necessary, mix the core and bypass stream in the turbofan engine if necessary. So, fighter planes which are say low bypass ratio engines, where the nozzle before the flow to we exit from the nozzle, it will get mixed. Okay. It allowed the thrust reversing as a part of thrust component in the forward direction, and that is what will be helping in terms of braking. It should suppress the jet noise and infrared signature. Thrust vector control if required to carry out say different kind of complex maneuvers. So, as I told, like this thrust vectoring, that is what is people they are using for say fighter aircrafts, where they are looking for all different kind of maneuvers, and it should be able to incorporate noise absorbing material. So, these all are the functions as listed by say nozzle. Okay. Now, let us try to look at what we mean by nozzle. Here in this case, suppose I say I am having my entry Mach number, that is what is subsonic, and if I want to accelerate my flow, when I say I want to accelerate my flow, that means I want to increase my Mach number. In order to achieve that, we need to have our passage to be converging passage, where at the exit you will be having higher velocity and my pressure will be lower, and that is what is defined as a subsonic nozzle. So, it says like nozzle pressure ratio in the range of less than 2, this subsonic nozzle, that is what has been used. So, that is called your conversion nozzle. This conversion nozzle, they are best fitted for say subsonic applications. So, when we say subsonic application, we must realize when we are not having any afterburner incorporated in turbojet engine, or if we look at our tactical aircraft or say modern subsonic say commercial aircraft, we are having this nozzle, the nozzles are of conversion shape. So, here if you look at, this is what is representing say conversion nozzle. Okay. Now, if we are incorporating the afterburner, so we have not discussed at this moment what we mean by afterburner. Basically, in order to augment the performance or in order to increase the thrust generation capacity of the engine, we are injecting the fuel at the exit of our turbine. So, the gas which is coming out from the turbine, that is what will be having sufficient amount of oxygen particle that are suspended, and if we are injecting our fuel, then that will get burned and it will be giving say constant pressure combustion, and by that mean we are increasing our entry temperature to the nozzle, and when we are increasing our entry temperature to the nozzle, we are able to increase the velocity with which the flow is coming out from the nozzle. But here we have constraints in terms of say nozzle pressure ratio. So, suppose it says if I am incorporating my afterburner, I will be having the nozzle pressure ratio something in the range of more than 3, and under that condition my conventional nozzle will not help, and we need to go with say variable area nozzle. So, here if I will be using the same nozzle, the maximum possible mass flow rate that is passing through the exit of my nozzle, it is restricted by m equal to 1. That is what is called thermal choking condition. So, once my nozzle, that is what is choked, no further increase of mass flow rate, that is what is possible with, and under that condition, in order to have higher exit velocity, we need to go with variable area nozzle. Okay. So, here if we try to look at, this is what is our fundamental equation for the mass flow rate for the nozzle, and if we consider for the choke condition, I will say here we are having say afterburner, that is what is being incorporated, and this is what is representing when I am not incorporating any afterburner. All other parameters if we put, they are constant for both the configuration, because my M equal to 1 condition, it is for the thermal choking. If that is the case, then we can say my area ratio without afterburner, that is what is my dry condition, and with afterburner, that is what will be the function of the temperature. Okay. And it says this temperature ratio will be in the order of 2. That means I need to have my throat area to be approximately 40% higher than that of my dry condition. Okay. Now, this kind of situation, that is what will be happening when I am having say transonic flight. Maybe my Mach number will be in the range of 1.2, 1.5. So, we can say for fighter aircrafts, this kind of configuration, that is what is required. So, we can say in place of using say your fixed area conversion nozzle, we need to go with variable area conversion nozzle. Now, let us try to understand what is the meaning and what all is the requirement. So, here in this case, suppose this is representing my free stream Mach number and this is representing my nozzle pressure ratio. It says if I am having my free stream Mach number in the range of 1 and if I will be going towards the 2, there is a rapid rise of say nozzle pressure ratio. So, we have discussed this point, say when my flow is subsonic, my nozzle pressure ratio will be in the range of something around 2, but when I will be going in a transonic range where my nozzle pressure ratio will be in excess of 3. Now, in order to understand that, we have our fundamental equation, that is what is available with us. This equation, if I will be putting say perfectly expanded nozzle where my exit pressure and atmospheric pressure, they both are same, then I can say that as my say ideal thrust. And let me introduce the parameter called ideal thrust coefficient. It is given by F ideal by P8 by A8. And here in this case, if we look at, it says this is what is representing my nozzle pressure ratio, this y axis, this represent my ideal thrust, and you can say for different nozzle ratios, we will be having different area ratios. So, here in this case, for say nozzle pressure ratio of 1.9, my area ratio equal to 1. Then later on, if I am increasing my say nozzle pressure ratio, my area ratio is going to increase. Okay. Now, let us move towards the next. If we say my nozzle pressure ratio is in the range of say maybe 1.9, under that condition we can say my exit area will be in the range of say maybe 1. So, here in this case 1 means, just look at, this is what is representing my conversing nozzle, this is what is my exit area, that is what is called my throat area. And as we have discussed, if we are increasing our pressure ratio, then we need to increase what will be our area ratio or pressure ratio. For that pressure ratio, I will be having the constraint with the sonic condition. So, I cannot increase further with my Mach number, but still if I am looking for very high Mach number, then I need to go with say conversion diversion kind of configuration. So, here this is representing my conversing passage, that will be followed by say throat, that is what is where I will be having my M equal to 1 condition, and that further acceleration towards the supersonic Mach number, that can be done by using this diverging passage. So, this area at the exit of my diverging passage, that is what we are representing as say A9. So, here if you look at, my pressure ratio is 1.9, I say my conversion nozzle, that is sufficient. If I will be going with say pressure ratio to be higher, my exit area is going to increase. So, here same plot we can say when I will be having my area ratio to be 1. So, meaning of this is I will be having A9 by A8 to be 1. Okay. Now, it says this is what is been increasing in downstream direction with the increase of the pressure. So, let us try to analyze this part. So, here in this case my gross thrust, that is what we have represented in terms of pressure and area ratio. Just look at here in this case, if we are moving towards say my flow to be supersonic at the exit, I need to go with say higher nozzle pressure ratio. If this equation I will be considering, say I am having suppose say my area ratio A9 by A8, that is what is suppose say fixed. If I will be putting that to be fixed, I can say this number, that is what will be remain constant, and it is not depending on what is my P infinity by P8. This P infinity is nothing but my exit pressure. Okay. So, we can say my nozzle, it is always been designed for one design condition. Suppose if I consider this is what is representing my nozzle pressure ratio and this is representing my design condition, and there I will be having my efficiency to be highest. Okay. Suppose say other than that, if I will be operating, then it says my thrust coefficient, that is what will be going to decrease when I will be moving towards a low pressure ratio. It will be increasing when I will be moving in the high pressure ratio. Let me put the point here. This is what is very important, and I feel we must have the detailed understanding of this. If I say this is what is my design pressure ratio, suppose if I consider I will be having my exit pressure, that is what is lower than that of my atmospheric pressure, that condition is defined as a over expanded condition where my exit area is too large. What is the meaning of that? We will be discussing very soon. I will be having second condition where my P9, that is what is greater than that of my atmospheric pressure or exit pressure. I will be having my area suppose smaller, then I say my nozzle, it is working under say under expanded condition. Okay. So, I will be having only one design condition with a change of pressure at the exit, I will be going under say over expanded condition or under expanded condition. So, let us try to look at here. Suppose if I consider this is what is my nozzle, what it says, it is going with the over expanded condition. When I say my requirement is the exit pressure, if my exit pressure and my atmospheric pressure they both are same, this is what is my requirement. So, I want my expansion to happen up to this pressure. So, I say this is what is my requirement. I am having my nozzle, that is what is having excess length, it is having excess area. Okay. So, here in this case, since my pressure, that is what is lower than that of my atmospheric pressure, under that configuration I will say I should have my nozzle to be truncated here, because additional length, that is what will be increasing the drag, and that is what is not my requirement. Now, what will be happening? Because since my requirement, that is what is getting terminated here, I am having additional length. So, my pressure that will try to match up with the pressure at the atmosphere, and that is what will be happening with our say shocks, that is what will be forming inside. Now, because of formation of the shock inside, we will be having the situation that my shock and my boundary layer they will be interacting, and that is what will be giving you unsteady flow phenomena, maybe some kind of flow rotation also will be happening, and that is what will be damaging our nozzle, and we can say this is what is most danger condition. So, we must realize what it says. Suppose say I am looking for my expansion to happen at particular pressure, but if I will be giving the excess amount of length, I will be having the problem, that is what is called over expansion flow, and that is what will lead to increase the drag, that is what is not my requirement. Okay. Same way, suppose if I consider say I am having my nozzle, that is what is having the length to be shorter. What is my requirement? I say I want to match my exit pressure and my atmospheric pressure. So, here in this case what is happening, I will be having my expansion, that is what will be taking place outside my nozzle. So, here if you look at, basically my expansion is happening outside my nozzle, and that is what will lead to say loss of my thrust. So, this much amount of thrust, that is what we will be losing. So, in order to avoid that situation, we need to have additional amount of length to be incorporated, such that we will be having efficient expansion. That is what will be happening inside the nozzle. This kind of trouble, that is what is not serious, and that can be analyzed correctly, but the thing is, if this is what is our scenario, we are having the issue with the thrust loss. Okay. Now, let us look at what is the meaning of that. As we have discussed, if I am increasing my free stream Mach number, I will be having rapid rise of pressure. Suppose say I am having two kind of nozzles available with me. It says like fixed conversion nozzle, I am having fixed conversion diversion nozzle. As per our discussion, we can use the fixed conversion nozzle for the subsonic cruise condition, and we can use, if we are looking for supersonic condition, we need to go with say conversion diversion kind of nozzle. Here in this case, if we look at, suppose if I say I am moving from takeoff condition to the cruise condition, my nozzle pressure ratio, that is what is going to increase, and under that condition we say my free stream Mach number, that is what is moving in this direction. So, in this particular region we can say use of my conversion nozzle, that will not give any benefit. Now, the situation is, it says if it is not the case, then we need to go with some other alternative. Other alternative, we will say okay, we will be going with the fixed conversion diversion nozzle. Again, for that configuration also, if we look at, we will be having the losses because of the expansion. It is over expansion losses, and this is what is giving the indication that we need to have our nozzle, that is what will be provided with the incorporation of variable area. Okay. So, here this is what is representing how we will be going with variable area nozzle. So, suppose if I want to extend my operating range for say fixed conversion nozzle, I can incorporate the variable area kind of configuration with which we can change the exit area. In line to that, for say conversion diversion nozzle, same way we can vary the exit area. Nowadays people they are talking about varying the throat area, that also is one kind of option. So, we can vary both, say we are having say variation of the throat area, we can vary the exit area. Now, this kind of problem mainly been happen in the case of when we are incorporating the afterburner. So, afterburner we are using rarely, but whenever we are using, it says it demands for variable area kind of nozzle. Here in this case, it says if we will be using variable area nozzle, we will be enhancing our performance in terms of thrust coefficient. Okay. Now, let us try to analyze this by using our control volume approach. Here in this case, we can say my entry condition is represented by state phi, and my exit condition I am putting as say 9. Here in this case, we can say there is no loss mechanism, there is no heat exchange, there is no work done, or there is no work, that is what is crossing this control volume. So, you can say my W and my Q, they both are say 0. So, under that condition, it says my delta E, that is not changing. What is the meaning of that? It says there is no change in total enthalpy. So, nozzle process, it is only converting my static energy into the kinetic energy. So, if you recall, when we were discussing about the intake, there also we were having similar kind of situation where we have discussed we are converting our kinetic energy into the static energy. Okay. Now, let us try to understand the expansion process which is happening inside my nozzle. This process is called expansion because at the exit I will be having my pressure to be lower. So, this is representing my isentropic expansion process from state phi to S9, and this is what is representing my actual process which is happening inside my nozzle. Okay. Now, the question is what parameter is of our interest. Very important parameter for say performance calculation is the thrust. And if we recall, if we want to calculate what is our thrust or the thrust generated by the engine, that is what is given by this formula. And in order to calculate that thrust, we must have what is our exit pressure and what will be our exit velocity. So, now the target is to calculate what will be our exit velocity. What we do? We will be taking our configuration here. So, we will be using our steady flow energy equation at state 5 and state 9, and if we will try to analyze this case, we will get our exit velocity, that is what is given in terms of this ratio. Okay. Now, let us try to analyze this part. As we have discussed, we will be having different conditions. We can say when my exit pressure and atmospheric pressure, they both are same, that is what we are defining as our perfectly expanded condition. We will be having say exit pressure, it is lower than the atmospheric pressure. Under that condition, my process it is defined as over expanded condition. So, you can see here my P9 is say P infinity, that is what is higher compared to my P9. Here in this case, my P infinity, that is what will be lower, which says my P9 is greater than that of my P infinity. So, in order to criticize this nozzle, we need to use the terminology, that is what is called say nozzle efficiency or adiabatic nozzle efficiency, and that is what is given by H05 minus H9 divided by H05 minus HS9. People they are defining that also in terms of velocity ratio. Okay. So, now let us consider this as our case. If we are putting say my process to be say isentropic process, and for that isentropic process we can represent in terms of my Mach number. Now, let me put this temperature ratio in the form of say my pressure ratio. Here we need to understand, we need to realize very important criteria what it says, like my pressure at the throat at which my flow is getting choked is defined as a critical pressure. Okay. Means there is no further rise of my mass flow rate, that is what is possible through that nozzle. So, that is what it says my M9 condition equal to 1, and under that condition my exit pressure, that is what will be equal to my critical pressure. So, if I will be putting my M equal to 1 condition, then this is what is representing very important criteria for nozzle, that is what is called say calculating whether my nozzle will be choked or unchoked. Okay. So, if we will be calculating this ratio, it says suppose if it is coming my critical pressure equal to my atmospheric pressure, then I say my nozzle is perfectly expanded nozzle. If we will be having critical pressure to be higher than that of atmospheric pressure, we can say my nozzle is choke condition, and if I will be having say my critical pressure that is lower than that of the atmospheric pressure, then we say my nozzle it is under unchoked condition. So, now let us try to understand how do we use that for our purpose. So, let us take the condition. It says in order to analyze, we will be first checking whether my nozzle is choked or unchoked. So, it says we will be using this formula for the calculation of critical pressure. Okay. So, P05 that is what is nothing but my pressure at the entry of the nozzle, that may be equivalent to what is the exit pressure from the turbine. So, we will be calculating that ratio. Here let me introduce the parameter, it is called nozzle efficiency. So, it says this is what is a way by which we can calculate when it is ideal condition, means we are considering our nozzle efficiency to be 100%. And here this is what is with say introduction of the term, it is called nozzle efficiency. Let us consider the first case, it says my nozzle is perfectly expanded nozzle. So, under that condition we can write down our temperature ratio T05 by T9, it is given by gamma plus 1 by 2. That is nothing but it is in terms of my say pressure ratio. In place of Pc I will be putting my P infinity, This will be helpful for the calculation what is my static pressure at the exit of the nozzle. Once we know what is our static pressure, we can calculate what will be our exhaust velocity. So, in line to that, if we are considering say actual condition, we need to incorporate the term it is called by nozzle efficiency. We can calculate what is our exit velocity. Now, let us try with the next condition when we will be having our critical pressure, that is what is higher than that of my atmospheric pressure. So, under this condition it says we need to consider the exit pressure equal to my critical pressure. Very careful. Suppose if I will be calculating my critical pressure and it says if it is coming greater than the atmospheric pressure, then we need to select my exit pressure equal to my critical pressure, and by that way we can put in the equation for the temperature ratio which we will be using for the calculation of our velocity, exhaust velocity. Similarly, for the actual condition we will be incorporating our nozzle efficiency term and we will be calculating what is our exhaust velocity. Okay. Now, let us try with the next configuration. It says when my nozzle is unchoke condition. So, it says my critical pressure, that is what is lower than that of my atmospheric pressure. Under that condition, my exit pressure we need to select as my P infinity. Okay. And if we will be putting that in terms of equation, we will be having the change in equation, that is what is given by 2 Cp T05 into bracket 1 minus P infinity by P05 to the power gamma minus 1 over gamma. And here in this case, for the actual condition you need to incorporate the nozzle efficiency. So, this V9, that is what is very important for us, because we want to calculate what is our thrust. Okay. Now, here in this condition if you look at, we say P9 equal to P infinity. So, in our thrust equation if we will be putting this as a equation, then my pressure thrust, that is what will be coming to be 0. Okay. So, we always preferred maybe our nozzle to be perfectly expanded or the choke condition. Now, different people they are using different terminology in order to assess the performance of the nozzle. One of the parameter they say as velocity coefficient. It says it is a ratio of actual velocity divided by ideal velocity. Ideal velocity, if we consider, it is representing the isentropic expansion process, but in actual my expansion is non-isentropic and I will be having the losses to be present, and that is the reason why we are considering actual velocity. Now, propulsion engineers they are primarily interested in what is the thrust, that is what will be generated by this nozzle, and that is the reason why they have incorporated the parameter, it is called nozzle thrust efficiency, that is nothing but my actual thrust divided by ideal thrust. Okay. Now, we know in ideal configuration we are considering our flow to be isentropic flow and one dimensional flow, but in actual condition that is not the real scenario, and that is the reason why people they have introduced the terminology, it is called discharge coefficient, that will be taking care of change of my mass flow rate in terms of actual mass flow rate to the ideal mass flow rate. So, nozzle thrust efficiency, it is also been rewritten in terms of measured thrust divided by CD into ideal thrust. So, what all we are using, that is what is been useful for defining the performance assessment of these all components. Now, let us try to look at what all we have discussed in week 2. It says we are having our components, we have seen, we have discussed different component as a inlet, compressor, combustion chamber, turbine and nozzle. We have discussed about the ideal behavior, we have discussed about the actual behavior. Suppose if I consider we are discussing about the inlet, where we have considered our process to be isentropic process ideally, where my temperature ratio is 1, my pressure ratio in the diffuser is 1, Later on in actual condition, we have realized my temperature, that's what will not be changing, but at the same time we will be having the change in terms of my performance of say P02. That is what is been calculated based on what is my diffuser efficiency. And here if you look at, this is what is representing my total pressure ratio. So, if we consider the figure of merit, it is nothing but the total pressure ratio or pressure recovery factor. Now, for the compressor, we have considered the ideal process to be isentropic process, where work done we have calculated in terms of mCp delta T0. The pressure ratio we have defined in terms of outlet pressure to the inlet pressure. Temperature ratio we have defined in terms of outlet temperature to the inlet temperature. If we are incorporating our actual condition, or if we are moving towards the actual condition, it says it is not the reversible process, and that is the reason why we have introduced the terminology, that is what is called say efficiency. It is called my adiabatic efficiency. We have also introduced the terminology, that is what is called polytropic efficiency. So, here in this case my figure of merit, if we consider, they are nothing but my adiabatic efficiency of the compressor and polytropic efficiency of my compressor. Now, let us discuss about the combustion chamber, or maybe when we say it is a burner. So, in ideal condition we will not be having any pressure drop, and based on my energy balance we are able to achieve what will be my turbine entry temperature. But in actual condition we have seen there will be loss of pressure, and also we have introduced the parameter, that is what is called burner efficiency. So, here in this case we are having the figure of merit as say my burner pressure ratio or loss of pressure and my burner efficiency. In line to what all we have discussed for our compressor, for turbine, we can assume our ideal process, that is what is say adiabatic, and reversible, that is what we say isentropic process, where we have discussed my work done, it is given by mCp delta T0, or you can say it is nothing but the enthalpy difference. And we have introduced the term, it is called expansion ratio and temperature ratio. But for actual condition we will be having the process to be irreversible process, and we have introduced the terminology, that is what is called say adiabatic efficiency of the turbine or isentropic efficiency of the turbine, and the more parameter we have discussed is a polytropic efficiency. Now, for the nozzle we have different kind of scenario where we are assuming our flow to be isentropic flow, and we have considered by nozzle pressure ratio, that is what is considered by calculating what is my say critical pressure ratio. Both the cases if we look at carefully, it says I will be going with the different configuration, different calculation, where we will be having our nozzle, is it in choke condition or the unchoked condition, and here very important parameter we have introduced in actual condition, it is my nozzle efficiency. So, if you look at, this is what all is giving very good idea about what all components which we are using for gas turbine engine, that is what is been applicable for the aircraft. Okay. Now, let us try to conclude what all we have discussed up till now. It says I need to go with the actual process, and that actual process, that is what is been defined in terms of efficiency. So, it says my diffuser efficiency, that will be in the range of 0.7 to 0.9. It is strongly depending on the Mach number. Now, the question may arise, what we mean by efficiency. Just realize one thing, when we are starting with say initial or very first step of the design for gas turbine engine, we are not having information, that is what is available. So, we need to assume these efficiencies. So, very first step we will be assuming the efficiency, based on that we will be doing all our calculation, and from that we will try to assess the performance. Based on that, as we have discussed in our first week, we will be going with the number of iterations in terms of cycle analysis to meet the specific requirement. Finally, we will be finalizing, or we are freezing all calculation, all parameter we have calculated, and we will try to make those components. Once those components they are being designed and fabricated, then it will be going for the testing, and again there we will be verifying this efficiency. So, very first step for the cycle analysis, it is to have the information about these efficiencies. So, mostly aircraft manufacturing companies, they are having their all information, that is what is available. We say that is what is database, that is what is available with them, and they are starting all their calculation based on those numbers. So, here in this case it says my diffuser efficiency will be in the range of 0.7 to 0.9. My compressor efficiency, that will be falling in the range of 0.85 to 0.9. The burner, that is what is efficient component, it will be having the efficiency in the range of 0.97 to 0.99. Turbine efficiency, we can say it is 0.9 to 0.95, and my nozzle efficiency will be 0.95 to 0.98. Now, the question what we need to answer is why we are not taking that as 1 or 100%. If we are taking this as 100%, we can say that is what is my ideal condition, but there need to be justification for the selection of these numbers. So, what is the justification here? So, in diffuser we will be having frictional losses, we will be having shock loss, that is what is present, and because of that it will be lead to reduction in the performance, that is reflected in terms of efficiency. Same way, if we are talking about the compressor, we will be having frictional losses, turbulent loss, separation, shock, bleeding, cooling, all this will lead to reduce the performance of our compressor. For turbine, we will, for say burner, we are having incomplete combustion, chemical composition, physical property, thermal losses because of conduction and radiation, say pressure loss due to the friction and the drag. That is what all lead to reduce the efficiency in this term. For the turbine, since it is working under favorable pressure gradient, again here also we will be having these losses because of friction, because of mechanical losses, because of shocks. Okay. And in the case of my nozzle, since it is a stationary body, we will be having losses because of presence of friction and because of shocks. So, here we are stopping with our second week. So, what all we have discussed, let us try to conclude that part. So, very first week we were discussing about the performance assessment. Now, slowly we are moving towards the control volume approach for different components. They are say inlet diffuser, compressor, combustion chamber, turbine, exhaust nozzle. For that we have discussed about adiabatic and polytropic efficiency for the compressor and turbine. We were discussing about the work balance, energy balance. We were discussing about various components and their requirement in gas turbine engine, which is applicable to the aircraft. So, I am sure by the end of this second week, we will be building the confidence in terms of moving forward. So, here we are stopping with the lecture. I request all of you to go through what all we have discussed in week 1 and week 2, because that is what will be very much required for our further weeks discussion, week 3 to week 12. So, stay connected with this course. Thank you very much for your kind attention.